limit comparison test uses limit to compare two series instead of inequality. So when it comes to choosing whether to use comparison test or limit comparison, it's usually limit comparison that you want to use. Inequalities are very hard to use. Okay? So here's the statement. If an is bigger than 0 and bn is bigger than 0, and if limit of n going to infinity of an over bn gives you some value c, which is non-zero, then summation of an and summation of bn converge, diverge together. Okay, this one, if you think about some examples, here's a trivial example. How do you show that summation of 2 over n squared converges? Well, limit of n going to infinity of 2 over n squared with 1 over n squared. Oh, if you divide by a fraction, it's keep, change, flip, right? So you keep this, change this division to multiplication, and you flip this fraction upside down. And these two cancel, so it's 2. So that means if summation of 1 over n squared converges, then this should converge as well. Okay? Is that good? Does this converge?
Yes.
Yeah, it's a p series with p equals to 2, right? So p series p equals to 2 greater than 1, so it converges. So we know that this converges. But this is not the way you want to use this, because you could just establish that this converges without using the limit comparison, because what is summation of 2 over n squared? 2 parentheses 1 over n squared, and we know that this converges, so this must, the one with 2 will just converge to twice of the other, right? So this is kind of useless. That's not the time that you want to use limit comparison. So let's try another example. Example 2. Well, this was an example that we did for comparison test, right? This time, I want to compare this with this. So I want to compare 1 over square root of n minus 1 summation with 1 over square root of n. Let's apply the limit n going to infinity. What's this limit? Well, again, keep, change, flip. You keep the top. Change the division by multiplication, and you flip this, so it's square root of n over 1. And when n is really, really big, this doesn't do much, right? So this is more like 1 over square root of n. This is like square root of n over 1. So what's the limit? No. This is more like limit of square root of n over square root of n. So that's 1, right? Which is not 0. If it's 0, then we can't make such conclusion. But yes?
So you wouldn't, so because like the square root of infinity is infinity, right?
No, if you say infinity over infinity, then that's an indeterminate form. You can't say this is 1.
Well, that's why I'm confused as to why it's 1, because if you plug infinity in for n, it just becomes like square
No,
root of-
what I'm trying to say is that when n is really big, this doesn't do much.
Right.
So this limit is same as this,
Okay.
right? 1 times square root of n,
Mhm.
square root of n times 1, right?
Yeah.
But then algebraically, what is this?
Algebraically 1.
1, so this
Okay.
must be 1.
Okay.
Yeah. If you don't like that, we can actually do it better. I was just trying to skip some steps, but the actual way to do this would be limit square root of n over square root of n minus 1. And then you can divide top and bottom by square root of n, which gives you limit n going to infinity of 1 over 1 minus 1 over square root of n. But what is the limit of 1 over square root of n?
0.
Yeah, because square root of infinity is infinity, 1 over infinity is 0. So you just have 1 over 1, which is 1, which is not 0.
Okay.
All right, so if that's true, then what do we know? The convergence or the divergence of this given series is determined by the convergence or divergence of this series. And summation of n from 1 through 2 to infinity of 1 over square root of n diverges because it's a p-series with p equals to
1/2.
1/2, which is less than or equals 1. Okay? And since this diverges, this must diverge. Therefore, summation of n equals to 2 to infinity of 1 over square root of n minus 1 diverges by limit comparison test. That's the conclusion. But using this example, let's kind of understand why such theorems should work. What does it mean? Well, it means if n is really big, then these two are pretty similar. It's 1. So the ratio between these two are about 1. So when you're talking about n from, say, a billion, or let's see, 12 power is a trillion. A trillion. So n equals a trillion to 1 over square root of n minus 1. This is about the same as trillion 1 over square root of n, right? And what happens is that you're really worried about the tail of a series. See, from 2 to trillion terms, that's just some finite value, right? Of course, this will give you a bigger value there compared to this one, right? But when you get to trillion and then infinity and beyond, okay, say to trillion to infinity, then these two are about the same. And this converges, this should converge as well. And such a thing, like ignoring the first trillion terms and only looking at trillion and afterwards, that trillion and afterwards is called the tail of a series. And the idea is that if you are just concerned about whether a given series converges or not, you only care about the tail of the series. If you can show that the tail of series converges, then the entire series should converge. If the tail of the series diverges, then the entire series will diverge. Okay? So like you start from 1 million to infinity or 100 to infinity. You can just chop off the beginning 100 terms or 1,000 terms as you wish, and you only is concerned about the later part, the tail of the series. If that converges, the entire series converges. Okay, so you get the idea that this thing here, it means that 1 over square root of n minus 1, 1 over square root of n, is about 1 when n is really, really big. That's what this limit is saying. So having this summation and this summation for n really big will be about the same. So if this converges, then this has to converge as well. That's the idea. That's limit comparison test. And this is easier than straight up comparison test because you don't have to do inequalities. You just have to choose something that's comparable.